Alright, let's begin. We are talking about vectors here today in the matrix notation form and trying to provide some applications of matrix notation to economics. So let's start with vector equations. There is the simple vector which just a column with numbers. It might be integers, it might be rational numbers, and generally we assume that W1 and W2 are any real numbers. Set of all vectors with two entries is denoted R2. So if you see this thing, that just means that we are talking about two entries. If there is R3, there are three entries, or Rn entries inside our vectors. So two vectors considered to be equal if and only if their corresponding entries are the same. So generally, if let me produce something like, so if we consider these two vectors, would they be equal or not? How do you think? They consist of the same entries, but the entries are quite different, and it is obvious that these two vectors, the first one and the second one, they are not equal because they are ordered. In order to be equal, they should be ordered with real numbers in the same order. So we have to compare the vectors side by side and compare each pair of entries in order to make sure that these are equals. So given two vectors of u and v in this space, their sum is the vector u plus v obtained by adding corresponding entries of u and v. So what does it mean? Let's produce a couple of vectors and let's just calculate their sum, like 1 and minus 2, and let's say that here will be 2 and 5, and we need to perform the summation of these vectors. So in order to sum two vectors, we need to sum each of the entries, obviously. What will be the result here? Anyone? So first row, 1 plus 2. Obviously, and the second row minus 2 plus 5, and the result 3 and 3. So this is the resulting vector. We also may use some vector and some scalar, some vector u and some scalar, it is called number, and produce the multiplication of this number on the vector values and obtain the cu, like the multiplication of number on the vector. So what does it mean? If we have some vector, let's say 3 and minus 1, and we need to multiply this vector to some number, let's say 5, what will be the result of this multiplication in the vector form? So we need to compute the scalar times this entry, scalar times this entry. So obviously 15 and minus 5, this will be the combination of scalar c and the vector u. Okay, so this is the result. And this result is called cu, the scalar multiple. The second slide gives us the coordinatory rectangular system in the plane. I think you are very convenient with this kind of coordinate systems where we have the axis and ordinate, and where we just can place each vector with corresponding values. So if v is in space R2, it has to coordinate. It has coordinate A, which corresponds to the first abscissa coordinate, and it has the second one b, which corresponds to this one x2. So if let's say v is 2 and let's say 1, so v will be expressed with this vector. We just draw a line from the origin to here. And u has different set of numbers, and it is very convenient to understand that if we try to sum these two vectors, we just place this vector u over here, starting from vector v, and here is the result, which corresponds to the blue line vector. Is it clear for here or not? Okay? Okay. All right, let's then recall the previous slide for newcomers. Let's say we are given two vectors, vector u, which has two numbers 1 and -2, and vector v, which has two numbers 2 and -5. So let's compute something like 4 times u, then let's compute something like -3 as a scalar times v, and sum these values together, plus these values. Okay, times v. So I give you a moment to compute. Already raise your hands. So the first operation, 4 times u, will give us multiplication the 4 and -8. This operation to vector v will produce -6 and 15. And the addition of this vector and this vector will give us, the result will be -2 and 7. Okay. So this is the final answer for the question. So very obvious, very convenient, and just make sure that if we write something vertically, the vector which writes as a column vector, it doesn't mean that it is equal to a row vector. What I mean is the column vector which is written like this is not the same as the column vector which is the row vector which is written in the form of a row. These are different. Don't compare them. We always care about the shape of the vector, because when we will perform matrix multiplications, we really should consider the forms of our rows and columns together in order to produce the multiplication, because we can multiply row by column, but we cannot multiply column by row over here. Then let's return to our geometric descriptions. So how can we place on coordinate system some vectors which, let's say this one, 3 and -1? What will be the shape of this vector here in the coordinate system? 3 and -1. Yeah, it will go over here, and for x2, and it will go over here to x1. So let's start with, let's say this is 3. We're starting over here and we going down. So the shape of this vector will be over here. Sorry, I cannot draw lines, but maybe it will be something like this. Okay. How can I delete? Undo? Okay. So that let's get back a little bit. Please draw. Let's draw. Draw the shape of vector u plus v, where u is 2 and 2, and v is -6 and 1. So please draw this shape. You have to draw both vectors, and you have to draw the result and shade the region which covers with the result. If you need light, turn it on. Already. Just try his hands in order for me to understand. Okay. For those who ready the second theme, vector u is 3 and -1. Display u to u and -2/3 u on a graph. How can we display the same vector if we multiply the same vector on some scalar? The coordinates of the vector changes, but the same vector that means the same line. They just have different points. So 3 and -1. This is the initial point from the origin, and we can continue going here for 2u. And we continue to go backward in this direction for -2/3 of u. So that will be generally first point, second point, and third point. Here's 0. If any questions, ask. Yeah. 2/3. Yeah, we go backwards in this direction. Here's minus 2/3. Oh, in the previous one? Yeah, minus 4 and 3. Yeah. So here's minus 4 and here's 3. This is the resulting vector. What was it?
I think I have one.
If everything is clear, we can continue. Are you okay? All right. So vectors in higher dimensions. So previously we were considering vector which contains 2 entries. Now vector contains 3 entries. So instead of 3 and 2, it will be 1, 2, 3, or 3, 6, 5, and so on. So 3 entries inside the column. They are represented geometrically with the 3-dimensional space. So generally we need to consider 3 coordinates and draw something inside these 3 coordinates. It will be like the 3-dimensional cubes, rectangles, 3-dimensional rectangles, and our vector will be a line inside this 3-dimensional space. The same applies if we considering not R3 but Rn. We need to produce on our plane, on our 2-dimensional coordinate systems, additional dimensions, like 3, 4, 5, 6 dimensions. It is all possible, but it can, involves certain imagination to understand where it goes. So for these purposes, for demonstration in Rn dimensions, generally it is easier for you to program and let the computer display everything for you. But it is possible. For common people, it is easier for understanding 2 or 3 dimensions, but generally mathematicians can operate with higher dimensions and everything is okay. So for our purposes, we will not demonstrate Rn, but we will perform operations in Rn, and this is like normal thing. Okay, so there are, let me make it a little bit larger. Okay, there are certain properties, algebraic properties of Rn. So if we sum 2 vectors together, it doesn't matter where they stand. So we can sum first plus second or second plus first vector. We also can move the brackets, the transcendental rule. It doesn't matter where we move our brackets in our summations. We also may sum with 0 element and produce the same vector. It doesn't change. If we sum up with the opposite element, we will get 0. If we multiply the scalar number on this summation, we can use the normal computations, like if it were ordinal numbers. The same thing applies here and to the rules 7 and 8. So multiplication on 1 or on the vector of 1s doesn't change elements of the original vectors. So these are really pretty obvious rules. You just consider your vectors here as numbers, as the vector of one number, and you apply all these rules like in school math. What is more important to use with these rules is called the linear combinations. So generally we have several vectors and we have several scalars. And generally it doesn't matter that Rn or not Rn. These are just how many elements we have. In Rn we have n elements for our columns. So linear combinations is the multiplication of each scalar on each vector plus this scalar on this vector plus the last on the last. So this is the sum of multiplication. Okay, linear combination is this thing. It is a sum of multiplication, sum of products of vectors and their scalars, or these scalars are also called weights. The weights in a linear combination might be anything, like they might be even zero, even real numbers, anything. So something like we have vectors v1 and v2, and we produce the 3 to the power of 0.5, let's say. So 3 to the power of 0.5, this is a square root of 3 times v1 plus v2. This is normal. Or 0.5 times v1 equal to 0.5 v1 plus what? What should we add to make this equation stands? So according to our rules, it is obvious if we add something which is 0, it doesn't change this equation. So we can produce 0 v2. And how can we make 0 with the summation? Many possible ways, but obvious way including 0, 0 v1 plus 0 v2. Okay, to get the result in 0 over here. So these linear combinations can be really good demonstrated using the plane. I hope I have them. No, I don't have them. Okay. Let's then consider this example. 1 minus 2 and minus 5, 2, 5, 6 and 7, 4, minus 3. We need to determine whether B can be generated as a linear combination of A and 2, A1 and A2. So what does it mean? That means just a production of x1 times a1 plus x2 times a2, which is equal to b. That means we have determined how can we generate b with this combination of a1 times some coefficients. So the idea is to just calculate these coefficients. So how can we do that? Let me rewrite this example in Excel and I'll show how to do that. The idea is we need to just calculate what will be the values for x here. Okay, so we had initially vector a1, which is 1 minus 2 and minus 5. This is vector a1. We have vector a2, which is 2, 5 and 6, and we have vector b, which is 7, 4 and minus 3. We need to produce this result, x1 times a1 plus x2 times a2, and equalize it to b. That means we need to write down the vector equation with scalars inside. So let's just assume that x1 is the scalar and we multiply x1 on this vector a1. What will be as a result of multiplication? It will be x1 instead of 1, and it will be minus 2x1. Let me use minus 2x1. And here will be minus 5x1. So we just multiplied x1 on this vector. Then we add accordingly, x2 times this will produce 2x2, 5x2, and 6x2. Okay. And of course, we need to equalize this with our numbers over here. Seven, 4, and -3. And here, when we see this inside the vector form, so I assume that you understand that we have here these squared brackets, which denotes our vectors. Plus square bracket over the second vector equals square bracket. So we have square brackets around all this. And now we are able to distinguish the vector form to just system of linear equations. It is also quite obvious, I think. X1 plus 2x2 equals 7. The second equation will be 2x1 plus 5x2 equals 4. And the fourth equation, okay, tries to compute. Minus 2x1 plus 5x2 equals 4. And minus 5x1 where's x? 6x2 equals -3. So here we have all our three equations, and now we are dealing with the system of equations. How can we solve this system? We can rewrite the system into a matrix form. Who remembers how we do that? So this system consists of two x's and the right-hand side. That means, let me just copy over here. Okay. So we rewrite this system. Do you see it? X1. Okay. We inside the matrix form. So here will be 1, here will be 2, and here will be 7. The coefficient in front of x1 is 1, the coefficient in front of x2 is 2, and 7 is the right-hand side. Accordingly, -2, 5, and 4, and -5, 6, and -3. So this is the matrix which we obtain from this system. Let me change the number. Okay, so this is the matrix which we have obtained right now. Now the goal is to solve this matrix to find out what will be x1, what will be x2, what will be x3. In our last lecture, we demonstrated that we are starting with our first row, and we're starting with the first element. It is quite convenient that we have 1 over here, so we need to somehow change these two values to zeros. And our first step will be summation of 2 times this row plus this row, and 5 times this row plus this row. Okay. So our first operation will be multiplication of 2. Be 2, 4, and 14, and we add with this, and we got 0, 9, and 18, and then we return our initial values. Yes. Okay. And then we multiply by 5, and here will be 0, 16, and 32. This is our initial step. Our second step is to select the second pivot element. Obviously, it will be this one. And in order to get it a little bit easier, we can divide the whole row by 9. So instead of 9, there will be 1, and here will be 2. Okay. It's quite obvious that we can do the same with the last row. We just can divide with 1 and 2 over here. And as soon as we can see that we have the same 2 rows, then the last one is obviously will be zeros. So from first row times, from the second row times minus 1 plus third row, and the third row will be whole zeros. So what we have got free x free. Free x free. Okay. So the solution for our system, let me also change these elements a little bit. There will be 0 here, and here will be 3. So this is the final solution for our system. So x1 will be 3, and x2 will be 2. This is x1, okay, x1. This one is x2, and this is b result. Result was b, yeah. So x1 equals to 1, x2 equals to, okay, x1 equals to 3, x2 equals to 2. And x3 is 3. So now we are able to write the answer x1 and x2 to our b can be generated as a linear combination of a1 and a2, where x1 is 3 and x2 is 2. So our initial example over here was written 3 and 2. Okay. Let me make it a little bit smaller in order for you to capture all the details, and just move it over here. So this is the whole example. As a follow-up to this example, we can write the rule. Obviously, we specified that 3x free. Let's write this rule. A vector equation, which is in the form as we have just considered, has the same solution set as a linear system whose augmented matrix is in this form. So what we actually did in our example is we formed this a linear system. First, we started from the vector form. We multiplied on the coefficients x1 and x2, produced the linear system. From the linear system, we wrote down the matrix, and we obtained this augmented matrix. Augmented means we add the right-hand side inside our matrix. So B can be generated by linear combinations of these vectors only if there exists a solution to the linear system corresponding to this matrix. And there is such solution. We have found the solution for x1 and x2, and we produced this matrix as a linear combination. Any questions? Okay, then let's continue. So one of the key ideas in linear algebra is to study the set of all vectors that can be generated or written as a linear combination of the set of vectors v1 to vp. So now we considering this new word for you. This is the span. The span where we have the set of solutions, and we spanning or expanding this set of solutions over the whole possible combinations of numbers. So if we have had this kind of, I don't actually remember, but I suppose that there was this kind of vector and there was this kind of vector, and we sum up and had this rectangular group. Smaller. So we had this rectangular span is something if we move this set of possible solutions to all directions, we expand it. Okay? This is the span for our rectangular form. We might have the span also for the lower side, this line. What will be the span for this line? Okay. So to both directions, we just span this whole set of solutions. What does it mean? As you can consider, this is one, this is 2, and this is -2 to 3. So we expand over here to the infinite, and we expand over here to the infinite minus. This is the expansion. So here we also consider all the sets of combinations in order to produce this expansion. Okay? So this is like the key idea. If you are considered to find the span, you need to find all possible combinations of x's in order to produce this thing. So the span, let it be, it's not very good actually, not very good picture, but it was initially some small vector, and it is expanded to some bigger vector, okay? Or maybe on the rectangular set, if we had the solution for u and v, we expand this solution to u and v with all possible values. Okay. So here is just for picture only, we limit it with 0. Generally, we are not limited with 0, we expand for all possible solutions. Okay? Let's produce the example. The example is like this. We have vectors a1, which is 1, minus 2, and 3. And we have vector a2, which is 5, minus 13, and minus 3. Okay, let me change. And the vector, the result is a vector b, minus 3, 8, 1. Span for a1 and a2. a2 is a plane through the origin of our 3 dimensions, because we have R3 dimensions, is a plane. In our R3. And the question is, we know that span is a plane. Does B belongs to this plane or not? Is B in that plane? So the questions like this are very common for linear algebra. What does it mean? Does the linear combination of vectors a1 and a2 produces b? What does it mean? If linear combination produces b, that means that the system has a solution. So the retranslation of this question, is b in that plane? That means, does the equation x1 a1 plus x2 a2 equals b or not? So this is the same question. Equals b has a solution. Let's change this sign over here. So to answer this, we again form the augmented matrix. Let's form it. Whoa. This is the second and these are the third. So this is our augmented matrix. And now we need to produce the, again, very convenient pivot element. So the first option will be 1, 5, minus 3. What will be the second and the third? Please compute. Done? So in our first step there will be 0, minus 3 and 2. In our third step there will be 0, minus 18, 10. And then we reproduce this equation as 1, 5. I move a little bit. Here. 1, 5, minus 3. 0, minus 3, 2. 0, 0, minus 2. So the third equation has this value. x2, 0 equals minus 2. Okay? So which shows that the system has no solution. Here's x1, here's x2, and here's b. So x2 0 equals to minus 2. This is impossible. So the system has got no solution. That means the initial vector x1 a1 plus x2 a2 equals b has no solution. So b is not in span a1 and a2. Okay.